In this video, we're going to start our conversation about motion by getting into Newton's first law and something called net force. This is going to be a technique that we're going to use to help simplify many forces down to one single force that we can then use later on in our next lesson. Before we can really get talking about forces, we need to talk about how we're going to quantify forces in this class. You've probably heard of Isaac Newton or Newton's three laws of motion. Well, we also use the name Newton to describe our forces. We're going to use this as our unit of force. So if you're pushing on a cart with 20 newtons of force, we'll just write that as 20N. The capital N represents a newton. Now, Newton, is a derived unit. You might remember from our conversation of units several weeks back that we can have units that are fundamental units, kind of like the primary colors in our color scheme. So things like meters, seconds, kilograms. There are 7 fundamental units. Now, these fundamental units can be combined in different ways, like primary colors to make secondary colors. Primary or fundamental units can be combined to make derived units, like a newton here. So a newton is actually a derived kilograms times meters per second squared. All 3 of these units are fundamental, so you can see where the newton comes from. In our next lesson, we're going to talk about exactly how this unit is related to an equation relationship that we know. But for now, just know that newton is a derived unit. We don't use newtons too much in our everyday lives, so it's useful to have some conceptual model, a reference point, when we talk about newtons and how big they are. So I'd like you to imagine that you're holding an apple in your hand. This apple is pushing down on your hand because of the force of gravity, but your hand is also pushing up on the apple. Equal and opposite force. Turns out that force is about 1 newton. Obviously, it's going to be different depending on the different size of the apple. But I think this is a useful analogy here, or a useful reference point, because if you are given a problem that says you push with 20 newtons of force, without any conceptual reference frame, it's hard to know if 20 newtons is big or small. But now you know that 20 newtons is pushing the same amount as you would have to push up if you were carrying a basket of 20 apples. So it can be it's kind of a weird analogy, but a useful one to know what is a big amount and what is a small amount when we talk about forces in newtons. The other thing that I want to review here before we jump in is this idea of vector and scalar quantities. In our motion unit, we talked about vector and scalar quantities in a variety of different ways, but the main ones were displacement versus distance and velocity versus speed. The key difference here, a vector quantity has a direction to it. I also previewed then 2 units or quantities later on that we'd be hitting, force and energy. Now we're going to be getting into the force side of things. And these vector quantities with a direction, we sometimes called negative because we said up is positive, down is negative, and we use the direction to help indicate the sign. Versus scalar quantities were always only going to be positive. So that means when we're talking about force, we need to factor in direction. We don't always use the positives negatives here. So in this unit, we're not going to be quite as particular on this positive negative way of describing direction because our direction is often more complicated than that. So a force could be up, down, left, right, or even at this angle. And oftentimes we're going to have many different directions in 2 dimensions or even 3 dimensions that a positive negative doesn't fully describe what we need. So typically we're going to describe force just using a vector to show which direction it's going, or we might be asked to present the force just as the magnitude of the force. The magnitude of the force is the amount, the newtons, without worrying about the direction at all. So now we can get into Newton's first law. You might remember this is a pretty famous thing that is an object or body at rest will remain at rest or will remain moving with a constant velocity unless acted on by an unbalanced force. We see this in a variety of different ways, and it has to do with this idea that objects don't want to change their motion. If they're not moving, they want to keep not moving. If they are moving, they want to continue moving. Now, a great example of this is the classic tablecloth trick. So let's watch an example here now. So it's possible that you've seen somebody do that tablecloth trick before. The plates want to stay where they are because they are an object at rest. They want to stay at rest. Now, if you were skeptical about that last part with the motorcycle, you are correct to be skeptical. This advertisement for a BMW motorcycle has been debunked by Mythbusters as seen here.
Stayed on the table.
One way that we can also describe this idea of an object at rest staying at rest, or an object in motion staying in motion, is using a term that we call inertia. The law of inertia is basically just saying that an object wants to keep doing whatever it's doing. So if it's not moving, it wants to stay not moving. If it's moving, it wants to stay moving. This tablecloth trick is a great example of not moving. I want to show you an example now of using inertia of an object in motion to carry out a task. Alright, so as you saw, an object that's already in motion wants to stay in motion unless there is some unbalanced force that's acting. For the rest of this video, we're going to focus on this concept of an unbalanced force. A way that we can describe that is by saying that it is the net force. Net is just a fancy way of saying it's the total force. So if you factor in all the forces that are acting and wanted to simplify it down to one, this is your force. It's the vector sum of all the forces acting on an object. So say we have an object here. We're just going to draw it as a box. And there are 3 different forces that are acting. 20 newtons to the left, 10 newtons to the left, and 8 newtons to the right. This 20 and 10 combine to 30 newtons. And then 8 newtons to the right. We can find a net force just by seeing how things cancel each other out. 30 minus 8 leaves us with 22 newtons. And that 22 newtons has to be acting to the left because that is where our surplus of force is acting. Now, if I change this 8 Newton force instead into a 30 Newton force, I find myself with a situation known as equilibrium. Equilibrium is when all the forces cancel each other out, and then we end up with a net force of exactly 0 newtons. Equilibrium does not mean there are no forces that are acting on an object. I am in equilibrium, and gravity is pulling down on me, and a chair is pushing up on me. Those 2 things happen to cancel out to give me a net force of 0. That is equilibrium. And we can use this concept to help us solve some problems. So if we have these window washers here standing on a platform, we can determine some things about this platform and the washers themselves. So here we have 750 newtons from the weight of guy 1. Weight of guy 2 is 800 newtons. And the weight of the platform is 900 newtons. All of that is pulling down. Now this platform stays up because there are 2 cables here. We got a cable that's supporting 1,350 newtons, and then a cable of some unknown tension T. They're not perfectly distributed, so this isn't necessarily going to be exactly that, but we know that all the forces must cancel out to give us a net force of 0 newtons. I would like you to go ahead and figure out what that missing force is. What is the tension on this side of that platform? There's several different ways that you can do this. One is just by looking at all the different forces and add them together. If we say that up is positive, these two forces added together minus these other forces should add up to 0 because the forces perfectly cancel each other out. Solving for your unknown, you should find that the total force of that cable, we'll call it T for tension, is 1,100 newtons of force. That example was nice because it was all in one dimension. So it was either up or down, and they just cancel each other out or they didn't. Now let's add some examples where we have more than one dimension. We're in 2D. So we have some horizontal and vertical forces here. The first example is when things are actually pretty nice and cancel out for you. Here we've got 11 newtons going up, 11 newtons going down. So those two are going to cancel each other out. We don't have to worry about them at all. And then it just turns into a one-dimensional problem where we have 10 to the left, 14 to the right, ends up with a net force of 4 newtons pointing to the right. Sometimes, though, these forces don't cancel out. So if instead of 11 newtons going up, I end up with 8 newtons going up, these don't cancel each other out perfectly anymore. So we need to look at the horizontal and the vertical components separately and simplify things down. I've drawn another diagram here that I'm going to draw a simpler version of these forces. First, looking at these vertical forces, they simplify down 11 and 8 to 3 newtons going down. Likewise, these 10 and 14 simplify to 4 newtons going to the right. And if you imagine that you and your friend are pulling at a box, one is pulling to the right and one is pulling down, the box isn't going to go perfectly to either of you. Instead, it's going to go downward at an angle. Maybe a little bit more to the person pulling 4 newtons than the person pulling 3, but it's going to move at this angle. This is our net force. It's the combination of these two. And it's not as simple as just saying 3 plus 4 or 3 minus 4. Instead, we have to add these up in the form of a triangle. So I'll show you a cool animation here. Moving these around, these vectors can actually form a right triangle. Basically, it's just moving this 3 newton over. So I end up with a side of 4 and a side of 3. This right triangle gives me a hypotenuse here. And you can use Pythagorean theorem, a squared plus b squared equals c squared, or recognize that this is a Pythagorean triple. It's a 3, 4, 5 triangle. So this missing vector here is 5 newtons. So I can simplify this and just draw that vector alone. That is a net force of 5 newtons. So if we have remaining forces, both vertically and horizontally, we have to combine them in the form of a right triangle to find what we call the resultant vector. Sometimes we are going to have to use our SOHCAHTOA rules. If you remember SOHCAHTOA, it's sine is the opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is the opposite over adjacent. You're going to want a calculator that has sine, cosine, and tangent on it. And we are always going to be in degree mode in this class. So even if you're using radian mode in another class, you're going to want to make sure to flip it back into degree mode anytime you're using these trigonometric functions in physics. So an example that we're going to need for this is when we have a force at an angle. Looking at this right here, it's not going to be easy just with these two forces to simplify it down. I can't perfectly cancel out a vertical. I can't combine them in a right triangle because they're not at right angles to each other. So instead, what I'm going to do is I'm going to change this vector here so that it's no longer at an angle. Instead, I'm going to split up into 2 vectors, one that is horizontal and one that is vertical. I know in this case that this vector is at 30 degrees from the horizontal. So that's going to be useful to me because part of this vector is in the horizontal direction. I'm drawing that here green. So it's as wide as this angled one is wide. Let's call that x. I can also draw a vector that is as tall as this angled one is tall. We're going to call that y. So now you might notice we have a right triangle. X and y are by definition perpendicular to each other. So I have a right triangle. I can use SOHCAHTOA and this angle to solve for what I don't know. First, the reason this is going to be useful is now, instead of using this 20 Newton vector, I'm going to redraw this with just the x and the y in its place. Check this out. So now I have another diagram where I've got the y, the x, and this 10 Newton force that I knew ahead of time. So in order for me to simplify this further, I need to figure out the magnitude of this y and this x. And to do so, I'm going to use SOHCAHTOA. To find x is the adjacent side to this 30 degrees. So the SOHCAHTOA cosine is cosine of 30 x over 20. If I wanted to solve for x, I just multiply both sides of that by 20. So I get x is equal to 20 times the cosine of 30, which is about 17.3 newtons. If I do the same thing for y is my opposite side. The sine is the opposite over hypotenuse. So the sine of 30 is y divided by 20. Y then equals 20 times the sine of 30, which is 10 newtons. Now, this is my diagram. I know all of the magnitudes. Everything's either vertical or horizontal and should cancel out accordingly. And in this case, it perfectly cancels out in the vertical. 10 and 10 newtons cancel each other out. So really all I'm left with is one net force vector, which is 17.3 newtons. So there aren't any other forces, so that is my overall net force, 17.3 newtons, pointing to the right. I should also be able to use this to help me find a missing force. So in the example that we saw earlier with the window washers standing on that platform, we were able to find a missing force because we knew the object was in equilibrium. Here, we're going to say that this object is in equilibrium as well, but it won't be quite as simple because we're not perfectly in one dimension. These vectors here are some vertical and some horizontal within that picture, because both of these are at an angle of about 45 degrees. Now, an angle at 45 degrees will help me determine the x and y components of each of these vectors. So just as we did before, we're going to draw in an x vector. It's as wide as this angled one is wide, and a y vector as tall as the angled one is tall. And to solve for these two values, I'm going to find x is just the cosine of 45 is x over 50, which means that x is 50 times the cosine of 45, which comes to 35.4 newtons. So I'll write that here. I'll also write it down below. Finding y is the opposite. So sine of 45 is y over 50, or y is 50 times the sine of 45, which is also 35.4. 45-degree triangle is going to be symmetrical on those two perpendicular sides. Since the other one is also at a 50 Newton 45-degree angle, I can just reflect that over. It's the exact same result. X is 35.4 and Y is 35.4. Now this is pretty busy, and I've got some duplicate information here because this 50 Newton force is the same thing as this X and Y. So I'm not going to draw the 50 Newton anymore. Instead, I'm going to redraw this as just the verticals and the horizontals. Oh, let's watch that again. It's beautiful. When this happens, I am left with a force going straight down that I don't know, forces going horizontally that are 35.4 newtons, and two forces going vertically that are 35.4 newtons. The horizontals are in opposite directions. They cancel each other out. So I'm left with two vectors of 35.4 newtons going up and one vector that I don't know going down. If this is net force of 0, these have to cancel out. So this downward vector has to be 70.8 newtons. One more example here to go the opposite direction. If I know that this sine is 300 newtons, so that I know the downward force, I know enough information to figure out the tension on these cables, figure out these angled forces going up. I'm going to make an assumption here that each of these cables are supporting the same amount of the weight, which means that this 300 newtons has to be divided into 150 supported by the left, 150 supported by the right. Unfortunately, it's not as easy as just saying the answer is 150, because this is a vertical force, and these are always going to pull in the direction of the angle that the rope or the cable is at. So I'm going to draw this out as a vector, a force going at this angle here. It's going to have some horizontal part, some vertical part, and the angle is going to be 30 degrees. This looks slightly different here. The 30 degrees is showing on this side, but it's the same 30-degree angle. You can use your geometry proofs to find that. Now, why this is important is, as I mentioned, this 300 newtons is straight down, which means the only part that's counteracting that is this red vertical vector here. And we said that each one is going to take half the load. So let's call this 150 newtons, because that is half of the weight, is evenly distributed. So now I have actually enough information to find F, the tension of the cable, because I know that the opposite side is 150 and that the angle is 30. Sine of 30 is 150 over F. So if I wanted to find this, Ft, or F is multiplied by sine of 30, equals to 150. If I want to find F by itself, F, or Ft in this case, is 300 newtons. That leads to an interesting picture that all the forces are 300 newtons counteracting each other. And the reason for that is vertically they are still only supporting 150 newtons. Horizontally we didn't figure it out, but they are going to counteract each other. So each one is supporting the same amount of vertical weight, and relates to this problem as an equilibrium sort of situation. So where that leaves us is you should be able to define a force using these proper newtons, or proper units of newtons. Describe Newton's first law: an object at rest stays at rest, object in motion stays in motion, unless an unbalanced force acts. To find that unbalanced force, you should be able to find the net force on the object, and then you should be able to calculate that unknown force if there's an object in equilibrium, like we did in the last couple problems.